Hello, this is Ali, and today I'm going to talk about logistic regression. So logistic regression is again used to estimate the probability that an event will occur as a function of other variables. So it is very similar to the linear regression, but the difference is that the output of this model is actually a probability score, which can be used to classified into two or more classes. So, for example, you want to get the estimated probability that a borrower will default as a function of like their credit score, income, etc. Then you could use the regression. So the input of this model is the predicted variables, which can be again continuous or categorical, and the outcome is categorical. For example, it can give you no default or default. So this is something that can be done through a threshold, but it also gives you the probability. So the output is by default the probability score, and also it will give you a set of coefficients that can tell you what is the impact of each input variable to the output variable. It can be used as a classifier. So you could assign a class label to each of the probability scores that are given at the output. For example, like a high probability of a default will lead to a default label. You can use this logistic regression for binary class outputs. So binary means you can only have two options. Maybe a positive, usually a positive and negative case, or like a default case and non-default case. So for example, some examples are a customer will purchase something or not, or a borrower will be default or not, a politician will vote yes or not. So there are different ways that you could kind of model the output. So one way is binary. The other way you could model the output is if you want to have multi-class outcomes. So if there are more than two options, like a politician will vote yes, no, or just they don't vote, or a customer will purchase, not purchase, or purchase later, these are some of the classes that you could use to create a multi-class classifier. So if you want to use a regression model that actually gives you more than two categories, then you're going to use multinomial logistic regression. It's used when the dependent variable has more than two categories. So the logistic regression is based on a function, the logit function or logistic function. So this function, you can see that function here, f of y equals e to the power of y over 1 plus e of y. And the beauty of this function is that you could just give it any number from negative infinity to infinity. And the only difference, like one of the main differences we have compared to linear regression, is that the expression in linear regression is here, and that expression is actually given to the logistic function. So the output of this function is actually between 0 and 1. So no matter what number you give it, it gives you a number output of between 0 and 1. It kind of compresses the output and gives you like a probability like a score. So it will actually estimate the probability of an event occurring, and so each of these inputs are x of i's are actually your input features. And then we have the weights here as well. So these different weights are going to give you the relative impact of each input variable. So if your function, the expression goes towards negative infinity, then the logistic function will be 0, and if it goes towards positive infinity, it will be 1. So the way that it's going to work is that the default score, which is something between 0 and 1, and then we were going to use a threshold to set that, will be the f of all those different variables that you have. So it will be a function. It will give you the default, like whether a customer will default or not, based on a function of different inputs. So it's a supervised method, so you have to give the outcome variable whether it is 0 or 1, and the output of the function is 1 if the borrower will default, and not 0 if the borrower will not default, or any other case. In this case, that's it. If usually this one, number 1 is the output of 1 is the positive case, 0 is the negative case. So you could find the fittest model that estimates the coefficients of WIs, similar to linear regression. And then when you apply the fittest model to the test data set, you'll get a probability. If the probability is more than a threshold, which you will set, for example, 0.5, then you'll say that the borrower will default. Otherwise, you'll say that the borrower will not default. So you could change this threshold. A different threshold may actually be chosen. We're going to talk about that later. So when you put all these probabilities for like the histogram of all these probabilities for different actually cases and samples, you will get a diagram like this, which is the distribution of the defaulters and no defaulters. The blue are the defaulters, and you can see that the model for defaulters gives a probability of close to 1, and for non-defaulters close to 0. But there is not a very clear distinction at 0.5 here. So sometimes you may want to choose a different threshold based on what you're looking for. If you're looking for like pure defaulters, then you're gonna set it a little bit higher. Maybe the threshold could be over 0.8 if you're looking for like 20% of the overall defaults, or you could just change the threshold. And changing that threshold will change the accuracy of your model, precision of your model, true positive rates and false positive rates. So we're going to talk about that in the next lecture. So logistic regression is basically giving you that score, and then you could just do anything you want with as a score, probably set a threshold, and create a class output out of it. So when you want to check to make sure that the logistic regression model is actually learned properly, you could say, take a look at the signs. Does the signs make sense? Maybe there's a wrong sign, like a positive or negative sign might be in an indication of correlated variables. So you may have two variables that one of them has a positive sign as for the the weight and the multiplier, and the other one might have a negative one to negate the effect of that correlated variable. So make sure that you take a look at the signs and the weights to make sure that it makes sense. Are some of the signs are excessively large? Again, you might have correlated variables, or maybe the outcomes are for a subset is perfectly predicted, but not for the whole class. Maybe you need to have more classes or other subsets of your data set. So you want to make sure that the model predicts well on the test data, the data that it hasn't seen, and make sure that you evaluate it on that model and don't just use everything that you have for the training set. We'll talk about that again. Make sure you do not you avoid overfitting basically on the training data set. You can have some you could add some terms like regularization to it to make sure that's not going to happen. And similar to linear regression, what we have a pseudo R squared. So pseudo R squared is a measure that is defined for logistic regression that you could use, and the formula is 1 minus the residual deviance of all the null deviance. You could calculate these based on the formulas below, and most of the software packages, they report you the pseudo R square, even the residual deviance and null deviance. You could just calculate those, and it will give you a score which is pseudo R squared that you could work on it and interpret it similar to R squared. So if the pseudo R squared is near 1, it means we have a good fitting model. If it's near 0, then it's going to be a model that may not be a perfect fit. So we're looking for a pseudo R-square that is near 1 to make sure that our model works well. So again, there are some reasons to choose logistic regression. It provides a relative impact of each predicted variables, which is a great way to have a model. It's going to be explainable to the users. It's robust with correlated variables, so it's going to be like mostly if you have correlated variable, it works. The signs may not make sense, but it's going to work. It also it gives you a consign representation with the coefficients. So the coefficients give you exactly what's happening in your model and what is the impact of each output. And one of the great features of it is that it returns the probability estimates of an event, like there are the estimates, but it returns the probability of them, which is good. You may use that, you may find that quite handy. So the caution is that if you have like a linear combination of if you have if your input variables are not independent of each other, or if they're not linear, then it's not going to work for you. So make sure that you avoid correlated, to some extent, correlated values. And if you have a set of variables that are actually correlate with each other in a non-linear way, then it's not going to be like logistic regression is not going to be the best option. Again, similar to linear regression, it cannot handle variables that affect the outcome in a discontinuous way, like a step functions 1, 2, 3, and does not work with categorical predicted variables, which have many different distinct values. For example, zip codes. Some other, like naive Bayes, might be a better classifier for that. Okay, that's it, and thank you very much. If you have any question, just comment below or let me know. Thanks.